Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. The lecture is on basics of time series analysis. And for this lesson, I will introduce estimation approaches for seasonality. This slide provides a snapshot of the basic modeling of time series. For the simplest time series analysis, the response data are y, t, the time-varying observations where t is the time index, for example, day or month. In order to account for trend and seasonality or periodicity, we decompose the time series into three components, mt, st, and xt, where mt is the trend, st is the seasonality, and xt is the time process after accounting for trend and seasonality. Xt is often assumed to be a stationary component. Most classic time series models assume that the time series process is stationary, and thus we need to first estimate the trend and the seasonality components, subtract them from the time series yt, then further model xt. In this lesson, I'll describe common approaches for dealing with a seasonal component. Not all time series have a trend, but for those which do, we'll need to correctly account for seasonality. In the basic time series model discussed in the previous slide, seasonality is an additive component and can be estimated from the detrended data if there is also a trend component. We can remove the trend using two approaches, estimation of the seasonality and remove it, or differencing the data which directly removes the seasonality. To estimate the seasonality, we can use a seasonal averaging or use parametric regression in two ways. First, we can fit a regression model where each of the seasonal group, for example, month of the year, is specified as a dummy variable in the model. If the periodicity of the seasonality has many seasonal groups, we fit many regression coefficients using this approach. Second, we can use a cosine sine function to fit the predicting variables, where the predicting variables are the cos and the sine functions for different frequencies. The first method is very simple. It takes all time series values corresponding to each seasonal group k from 1 to d and averaging them to get the wk. Note that here d is the periodicity or the number of seasonal groups. For example, if the seasonality is monthly, then d is 12, and one seasonal group corresponds to 1 month. Because we have that the sum of the seasonal effects st is equal to 0, the estimated seasonal effect for st is wt minus the average across all effects. One way to perform the simple averaging is through a regression model where each seasonal group's mean is estimated via an ANOVA type model as presented in the next slide. A linear regression model approach to estimate the seasonal effects st is to consider an ANOVA type of model where we group the data by seasonality group. If the periodicity is d, then we have d seasonal groups or effects. Thus, we treat seasonality as a categorical variable. To fit such a model, we need to set up indicator variables or dummy variables that indicate the group each of the data point belongs. When fitting categorical variables with d groups, we only include d-1 dummy variables if the model has an intercept. Thus, this approach reduces to estimating a linear regression model. This can be convenient since we have a trend. We can estimate the trend and the seasonality in one regression model. But the previous model can have many predicting variables. This regression model can have many predicting variables, particularly if we have multiple seasonalities, for example, month and week of the year, and or the periodicity d is large. For week of the year, we will need to have 52 different dummy variables, for example. An alternative approach to using linear regression without having many regression coefficients to estimate is to use a cosine sine model. In this approach, we assume a cosine curve for the seasonality specified by three parameters: the amplitude, which is how high or low the curve will go, the frequency f, which is the inverse of the periodicity of the seasonality, and the phase which sets the arbitrary origin on the time axis. The only known parameter in this formulation is f, since it is provided by the periodicity of the seasonality. The cosine curve is thus inconvenient for estimation because the amplitude and phase parameters do not enter the expression linearly. Fortunately, a trigonometric identity is available that allows reparametrization of the cosine curve as provided on the slide. Now we have a linear parametrization where beta 1 and beta 2 are the regression coefficients with the predicting variables given by cos and sine of 2 pi f. Conveniently, if the seasonality has different frequencies, for example, month and week of the year, we can use the same formulation for each of the frequencies and introducing only the regression coefficients for each frequency. Since we have both trend and seasonality, we can use the approaches discussed so far on estimation of a trend and seasonality to remove them in order to get to a stationary process. To do so, at the first step, we can obtain an initial estimate for the trend, remove it from the time series process, and the second step, estimate the seasonality. Last, remove the seasonality from the time series process and obtain an updated estimate of the trend. The method used in the step 3 can be any of the methods used to estimate seasonality, not only the averaging approach as provided on the slide. Since we use regression to estimate the seasonality and the trend, we can do so simultaneously. For seasonality, we only have linear terms in the regression model, regardless whether using the seasonal means model or the cosine sine model. However, the trend can be linear in the predicting variables if assuming a polynomial with known order, or it can be non-parametric. To combine both into one joint model, we simply use linear regression if both the seasonality and the trend are specified by linear terms, or we can use a semi-parametric model in which the trend is non-parametric, but the seasonality is added to the model linearly. Last, we can also use differencing to remove the trend and seasonality jointly. If we have seasonality or period d, the differencing operator applied to the time series yt means that we take the difference of yt and yt minus d. If we decompose further this difference, we also have mt minus mt minus d, which could also remove the trend if the trend is slowly changing. Generally, this method is recommended when the time series is observed over a long period of time to allow for differencing over long periodicity's seasonality. To summarize, in this lesson, I introduced approaches for estimating seasonality. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial System Engineering. The lecture is on basics of time series analysis, and for this lesson, I'll focus on a data example that will illustrate estimation of seasonality. In this example, we'll return to the data example where we study the average monthly temperature for Atlanta, Georgia. In this example, we have data for 138 years. And the question we'd like to address is there seasonality and trend in temperature in Atlanta. A first model we discussed in the previous lesson is the seasonal means model. In this model, we fit a linear regression model with dummy variables where each one specifying the seasonal effect of 1 month. This is equivalent with an ANOVA model where the data are categorized into seasonal groups. For this approach, as well as for the second estimation approach presented in the previous lesson, we'll need the R commands in the library TCA. For using the R functions in this library, we will first need to load this library using the library TCA command. I'll point out that if this is the first time when you will use this library, you'll have to install it. We'll use a season function in this library, which will create the 12 dummy variables corresponding to the 12 months. We can feed a model with intercept as in Model 1, where we specify the time series on the left and the seasonal dummy variables on the right, where those dummy variables will represent the month. But this model omits the January coefficient. In this case, the February coefficient is interpreted as the difference between February and January average temperatures. The March coefficient is interpreted as the difference between March and February average temperatures, and so on. Alternatively, for a simpler interpretation of the coefficients as individual seasonal effects, we can fit the model without an intercept as provided in Model 2. I'll provide a summary of this model in the next slide. Next is the implementation of the cos-sine model to create the two predicting variables, the cos and sine of 2 pi t for the frequency 1/2 or 1 per year. We can use the harmonic function in R, where the input is the time series and 1 stands for the frequency. Additional cosine functions or at other frequencies will frequently be used to model cyclical trends. For monthly series, the higher harmonic frequencies such as 2/12 or 3/12 are especially pertinent and will sometimes improve the fit at the expense of additional parameters. For example, we can use the model with 2/2 as provided in Model 4. One way to evaluate whether we will need additional cosine curves is by evaluating the significance of the model parameters or using a model selection criteria. This is a portion of the output of Model 2, the model with all dummy variables without the intercept. The estimated regression coefficients provide the means for each individual seasonal group. For example, the average for all temperature values in January is 43.02, and the average for all temperature values in July is 79. In order to get a seasonal effect, we need to subtract from each of the means the average across all of the estimated means. According to this model, July and August are the hottest months of the year, whereas January is the coldest. In the output, we also have the R-square, or so-called the coefficient of determination, which is an indication of the variability explained by the predictive variables in the linear model. For this model, the R-square is very large, 90.7%, indicating that seasonality explains most of the variability in the monthly average temperature over years. This is the output for the two models using the cosine-sine decomposition of the seasonality. The difference between the two models is that in the second, we're adding one more set of cosine harmonics. We can see from the output that the estimated coefficients for the first set of harmonics are similar for the two models. Moreover, the second set of harmonics with the frequency 2/12 have statistically significant coefficients, providing that the harmonics with the frequency 1/2 are in a model. The R-square is slightly lower for these two models as compared with the R-square for the seasonal mean model. Moreover, the adjusted R-square increases with the addition of the other set of harmonics, an indication that perhaps including higher frequency harmonics improves the fit of the seasonality. Here we compare the fitted seasonality for the two models to see whether there is a significant difference in the fit. For the first model, the seasonality is provided by the regression coefficients and expressed in the R code by the R function COEF of the fitted model, whereas for the second model, the seasonality is provided by the fitted values of the regression. We can compare the fit of the seasonality by overlaying into all the fitted seasonality into one plot. The plot is here. as provided by the R code, the seasonality fitted using the seasonal means model is in black and the sine-cosine model is in brown. As seen in this plot, both are very similar in fitting the seasonality. Because the fit is almost the same, we would prefer the model with fewer regression coefficients, particularly the sine-cosine model. In a different lesson, we found that there is a slightly increasing trend in temperature over time. With this, we would like to estimate both seasonality and trend jointly. We'll begin with the simplest parametric model where we consider a quadratic trend and seasonality model using the cosine-sine model. For this, we specify in the LMR command the response variable, the time series, or the average monthly temperature values, and the predicting variables for both the trend and seasonality together. In order to evaluate statistical significance of the trend and seasonality, you can further analyze this model. For example, one could test whether the trend adds any explanatory power for the model, given that seasonality is already in the model. Such evaluation method for linear regression has been introduced in the regression analysis course. Here we'll only plot the residuals introduced after removing the trend and seasonality, specifically subtracting from the time series the fitted values of the linear model. The time series plot of the residual process is here. In a different lecture, we'll study ways to evaluate whether such process is stationary, in other words, whether the trend and seasonality components have been removed. We can also fit a non-parametric trend along with the seasonality given that by the cosine-sine model. The GAM function in R allows fitting non-parametric and linear components jointly. To do so, we specify that the trend in time is non-parametric while not imposing any transformation on the seasonality, thus adding the harmonics to the non-parametric trend. Next, we compare the residual processes from both methods. Here is the plot comparing the residual processes, where in brown is the process for the parametric model, and in blue is the residual process from the non-parametric model. The differences are small between the two approaches. To summarize, in this lesson, I illustrated seasonality estimation using a data example. Thank you.